Today I'm going to be explaining the Euler forward method, explaining it with this visual graph. So what we're going to be having is a pursuer and a target. The pursuer is going to be in this plane, in this x and y plane, and is going to be trying to find this target in the fastest direction while this target is moving in this certain direction. We're going to be finding the distance between the pursuer and the target at each time step. And at every measurement, we want to check it. And we're going to be checking it by using the Euler forward method. So, by definition, it's a method for solving ordinary differential equations using the formula yn plus 1, which advances the solution from x of n plus x of n plus 1 equals x of n plus h. You'll notice we're going to be using this in our code to find the method increments a solution to an interval h, which is what we're going to be doing while using derivative information from only the beginning of the interval. As a result, the steps error is 0. This method is simply the Euler method. So, how are we going to be figuring this out? So what we need to do is we're going to import numpy as np. And what we're going to be doing a little bit different from what we've been doing in class is we're going to be using matplotlib.plotp. Yeah, very nice. Did it for me. And then we're going to run it. This is just going to import, allow us to make graphs in Python. And it looks a little cleaner and better, I feel like, for what we're trying to do. And I feel like it's easier to use it. I don't have to always say make subplots. We're going to define forward Euler method. What are we going to take in? We want to take t of x. That's a function of position for a target in the x position, function of target in the y position. And then we're going to have tx of prime and ty of prime. What is that? The speed of the x in target and the speed of the y in position, y in target. So, what else do we need in our function to take in these initial values? X of 0, start position in the x direction. Y of 0, start position in the y direction. We need a proportionality constant, which is how fast the pursuer is going relative to the target. That's what this constant derives from. We're gonna have our t range. What is the range between? We'll define that in the below, and then we're gonna have our n, which is the how many times we want to write this code. The more n's we have, the more accurate that this is going to be able to follow. Find what we're looking for. So we're going to define this t of h dot linspace t range, 0. We're going to start from 0, and then we're going to have t range, we're going to say from 0 to 1 from t, the target position of h. 0, 1, okay. And then we want it to increment the time steps, how much it's going to go by, depending on that value, and true. So what this is allowing us to do is going from 0 to 1. Let's say n is 10. It'll be 0.1, 0.2, 0.33, 0.4, 0.99. So depending on this n, what we give it, it's going to be how accurate it's going to be. So let's write a function for the speed of the target. And we're going to define it as a as a function of t. That's what this lambda means. And we're going to define tx prime is the speed of the target in the x direction. We're taking in the value of t. We're going to square it. We're going to plus it. We're going to copy this. then we're going to put it here. It's going to make it easier. T y prime times 1/2. So what this is going to be doing is going to be finding the speed. So you can see that's going to be the square root of the x and y. So what do we say x was? Tx of prime. We said that was the speed in the x direction, and ty was the speed in the y direction. We're just squaring it. We're just going to square it and take the square root of it. So we're going to find the speed. We're going to say b as a lambda as a function of tx and y. What is this one going to be used for? This is going to be essentially used for the distance between the pursuer and the target. Divided by b t x y. And we're going to be having c, which is going to be, f, which is going to be the derivative of the pursuer's speed in the x direction. So what we're going to be doing, we're going to be using the proportionality constant. We're going to multiply that by a of t The one thing you can mess up in this code is the parentheses, and we don't want to mess that up. Okay, parentheses here, t of y of t minus x divided by b t x and y. So we're going to have a f as a function of t, x, and y, k multiplied by a of t multiplied by t of y of t minus x, b t x y. We're going to copy this and we're going to paste it. And we're going to say we want to find the derivative of the pursuer's speed in the y direction. We can define that as g. So we already defined these certain values. We already have x and y, so we're going to have to name these. We're going to say g is in the x, the y direction. So we're going to change some of these values. T of x, t of y. I said t of x here. I meant x here. So I only have to change this one. Because I said f was a function of t, x, and y in the x direction, the speed. I'm looking at these parentheses right here. Looks good. I never checked it. Looks good. So now we're going to define y, np.zeros. We're going to need to store this in the y. We're going to define x. We're going to say np.zeros n. Store it there. We're going to say x of 0. We're going to say the first element. X is 0. Start position. We're going to say the same thing with y of 0 equals y position in the y position. And then we're going to say b is the distance between the pursuer and the target at each interval. But how are we going to define that? We're going to say b of the first element. We're going to say that's equal to b t of the first element x of the first element, y of the first element, So what it is. Oh yeah, just making sure it's working. Okay, a lot explained in a very small amount of code. So basically, B, what is this line of code going to be doing for us? Well, we're going to be needing to iterate. Now we just defined all our functions, but now we want to, what is it called? We want to implement the forward Euler's method. What that's going to do is it's going to iterate through this every increment, and it's going to check it until we find a certain value that's really, really small. That's a distance between the pursuer and the target. So what we're going to have to do is we're going to define y. We're going to say in the y direction plus 1. It's going to be y of j. It's going to iterate through this. We're going to use our h. That's what we found in Euler's method. That's defined. And then we're going to have j. And then we're going to have x of j, y of j, copying this code. We're going to say this for the x direction. We're going to say that's for the x. And for g, we're going to be putting the f, which is our derivative of the pursuer's speed in the x direction. I think that's all we need to change for that. And we also need to define b, j plus 1. What do we say? The distance between the pursuer and the target at each time step. It's going to iterate through that until it finds a value that is I'm thinking of a faster way to do this. If I just copy that, I'm just thinking, yeah, I should just copy this. And then if b of j is really less than or equal, let's say less or equal to 10 times to the -4, so a really, really small value, we're going to say, we're going to print that the pursuer, pursuer has been caught. Exclamation. And then we're going to break it. Just going to run that.